Good afternoon for some of you, and good morning for some of you as well. I'm Vinicius Viena Santana. I'm part of the Department of Chemical Engineering at the Norwegian University of Science and Technology, and I work at Ildefonso's lab. I'd first like to thank Professor Bentley for the invitation to be here with you today, and I'll be presenting a tutorial entitled Auto-completing Models to Uncover Missing Physics, a deep dive tutorial into universal differential equations. So before I actually start with the content, I'd like to give you a bit of a background about myself. So I started my educational journey in Brazil, where I did my bachelor and master's degree in industrial and chemical engineering from the Federal University of Bahia. And then I did my PhD in chemical engineering at the University of Porto, and being supervised by Ildefonso Nogueira and also Chris Calgas from Julia, that you know. So despite of my background in chemical engineering, I have always been passionate and about coding. And a couple of years ago, I also discovered Julia language, and also got really excited about it because it's a super nice programming language for scientific computations. So now I'm currently a researcher at NTNU here in Norway. As I told you, I'm part of Ildefonso's lab, which is a small group inside the process systems engineering group here at NTNU. So my research focus has been mostly on scientific machine learning and AI applied to industrial and chemical engineering. Yeah, so let me just keep track of my time here. Okay, so let's now move forward to the topic of this presentation itself. Much of you know that modeling is a key task in natural sciences, but yet building simple and powerful models can be very time consuming and expensive. So usually we have several options to build models in natural science, and these models, they vary in complexity and precision, and they usually compete for acceptance. So when you are modeling a system, should we favor rigor or simplicity, or should we prioritize exactness instead of usefulness? So if you would translate a model into a monetary value, we should ask ourselves, okay, should we favor our $10 model or our $1,000 model, assuming that the $10 model is the simplest one and the $1,000 model is our more complex one. So these are very popular scientists in the field of reaction engineering. Levenspiel, in a paper in modeling named "Modeling Chemical Engineering," he said, okay, in his view, the best approach would be starting as simple as we can, and then adding complexity to the model to the extent we need. So that means we should stick to our $10 model and then add complexity if we need to, right? So then by this a bit of context, we can ask ourselves, how can we do minimal extensions of our simple models that can make them better fit the observations we have? So if you're trying to model a system that is described by differential equations, then the answer for this can be the concept of universal differential equations that is discussed in this paper from Chris Kalkas and all the collaborators in 2020. And a very simple explanation of it would be, okay, I can put some small black box into my simple models and then excel in predictions. So here I brought a bit of an explanation about universal differential equations. So the universal word does not come from the fact that it explains everything in the universe. It comes from the fact that we are mixing differential equations with a universal approximator that aims to reduce the mechanistic model non-explained residual. So I have here my nice mechanistic model, which can explain the observation quite well, and then I can put some universal approximators into it to cover from the non-explained residual. So this universal approximator can be a neural network, and by the fact that neural networks are parameterized, we should be able to estimate these parameters. And to estimate these parameters, we have to set up an optimization problem. So now I'll move on from this general concept of UD into a more practical application of it. So I'll show you how it can be used in separation engineering. Because of my background, I'm a chemical engineer. It's specifically applied to fixed bed adsorption. So you may be asking, what's fixed bed adsorption? So fixed bed adsorption is a separation method And in this separation method, we use the difference of affinity of two components towards a solid phase to carry out the separation. So by introducing a mixture of A and B into the column, they pass through the adsorbent, and by the different affinities to the solid phase, they exit the column at different times. So that's the principle we use to separate substances in this kind of setup. So one of the most important quantities in these systems is what we call the uptake rate kinetics, which is basically telling us what is the amount of moles being transferred from the fluid phase to our adsorbent. So as you may imagine, the greater this number, the more it will take for a substance to go out of the column. So that's a very important quantity in this system. But if we try to describe the transport of chemicals inside what we call a fixed bed, we inevitably end up in a partial differential equation because things vary in time and also in the axial position, right? And if you try to estimate this very important quantity, the uptake kinetics, then I will have this quantity involved in a partial differential equation, which can get very complicated mathematical problem. So what people came up with is the method called the zero length column. And the zero length column is just, okay, I assume my column is sufficiently small, such as every gradient in the axial direction is negligible. And then that simplifies a lot the kinetics estimation problem and also the mathematical problem because I no longer have a partial differential equation, I have an ordinary differential equation. And here I brought to you this ordinary differential equation derived from the zero length column method. I have the fluid phase mass balance. So the rate of accumulation in liquid and solid phase equals what is coming inside my column minus what's coming outside my column. So I can also write down the solid phase mass balance, and the solid phase mass balance has this term I mentioned to you, which is the uptake kinetic rate. So that's an unknown function. So I can put this inside the solid phase mass balance, and I should figure out what is this function. So people came up with several types of function to describe the absorption kinetics. So for instance, people came up with what we call the linear driving force. So if you know Newton's law of cooling, you can recognize the similarity between this expression and Newton's law of cooling. And in fact, this Q star variable is the equilibrium concentration, which means in a similar way of Newton's law of cooling, Newton's law, it would be the environment temperature. So, but the fact is in absorption, we have no limitation to put a square here, or we can come up with very complicated expressions to sort of understand what's the uptake kinetics. And based on this background I gave to you, why not placing a neural network in this function instead of trying to guess what's the function of orb beforehand. So neural networks are universal approximators. So we are just putting these two variables inside of it and let the parameters be adjusted so I can learn the kinetics instead of trying to guess it beforehand. So a small observation here is that Q star is typically a function of the fluid phase concentration. So I have a function here inside of my neural network, not only a number. So now let's go on the implementation of a universal differential equation for this problem. I just wanted to make sure you understand the problem before I actually implement it. So the first step would be loading and visualizing my data set. So I'm loading here my package, PKG library. I'm activating my environment. So I have my versions of my packages load. I usually prefer to use the plots library to plot, and I also use the limited files to load my files that are written in CSV. So here I'm picking the plotly backend because it's nice that allows me to interact with the plots. So here I can load my data by using the read DLM function and then putting the separating element of my records. And then I can use the scatter and the plot functions from the plots library to visualize it. So here you can see this blue circles are my experimental fluid phase concentration. And here in orange, you can see this line, which represents the inlet concentration. So I give an inlet concentration of 20 milligrams per liter. And then the response of my system follows this typical exponential approach towards my inlet concentration. So, as I was speaking about universal differential equations, I have my universal approximator and I have my differential equation. So first of all, let me build my universal approximator, which is the neural network. And to do so, I'm using the looks.jl library. So first of all, let me just explain what will be the structure of our neural network. So as I told you, my neural network will have two inputs. So that's Q star, which is the equilibrium concentration in the solid phase, and Q, which is the current concentration, solid phase concentration. And if you remember, I told you that this Q star is usually a function of the fluid phase concentration. So the very first input node of my neural network is actually a function. So that's why I have put here this name of isotherm node, because this function that maps from C to Q star is named isotherm. And following that, we can have a pretty much a standard neural network architecture where I can put as many as intermediate layers as I want. And then this neural network is trying to estimate my uptake rate. So now we can see this in the code. So here's I'm importing looks library, and then I'm using the looks.chain function to chain the layers together. And you can see here that my very first layer is not actually a dense layer, but is actually a function I'm using to scale the parameters. I scale the inputs. So typically, when you're dealing with systems with engineering units, they have units that can be very far from -1 and 1 or 0 and 1. So when we work with neural networks, it's always a good idea to scale our inputs. So I'm putting here, chaining everything together, this pre-processing layer. So the nice thing about Julia is that, okay, I have this chain function. I can chain any function I want, including my scaling function. So now moving on to the neural network in itself, you can see that I have two inputs, and then in this intermediate layer, I have 8 neurons, and I'm using the hyperbolic tangent activation. Then I have a second layer with 10 neurons, and then also the hyperbolic tangent activation. And finally, I have my readout layer that map is from a 10-dimensional vector to a scalar. And here I can call the setup function, which randomly initialize my weights using some initialization algorithm. And then I can test if my function is doing the correct calculation. So I passed a vector with 2 dimensions as inputs, my randomly initialized weights, and I can see that it's returning me, which is a vector with 1 element, so it's a scalar. And now that I have defined my neural network, I have defined my U from the UDE model, I have to define my differential equation. So in order to build differential equations in Julia, we can use the differential equations.jl library. And I'm also using the diffq flux, which has binders for differential equation and neural networks. So this is a very standard approach for solving ODEs, not only in Julia, but also in other programming language like Python. So first of all, I have to build my function that has as inputs my dependent variables, my parameters and time, and this function should give me the derivatives. So in these first two rows, I'm building alias for my variables. So the first entry of my U vector is the fluid phase concentration. The second entry of my U vector is the solid phase concentration. And I have to calculate my Q star, as I told you, and then I can finally write down my derivative. So if you see these derivatives, they came from this mass balance I have shown you a couple of minutes ago. So you can pretty much see here where my neural network comes in. As I told you, I have two inputs in my neural network. I have Q star, which is dependent of C, and I also have Q, which is my another state variable, the solid phase concentration. So all these other parameters you're seeing here were defined. I haven't shown here in the presentation, it's hidden. But then if you exit the presentation, you can see the cell where they are defined. And then I have the solid phase mass balance as well, which is just derivative of Q with respect to time equals my neural network. So before actually training my parameters or actually finding the parameters, I can simulate the UDE to see how it performs with randomly initialized parameters, which should be really bad as expected, of course. So here to simulate my UDE, which is the differential equation, I have to set up my ODE problem. The ODE problem has as arguments my function that gives me the derivatives, my initial condition vector, which is given here with 0, 0. I'm basically say that my system is free of chemicals when t equal to 0. I have to set up my t-span, which is the time I will be integrating my ODE, and also have to give the parameters, which are the randomly initialized derivative work parameters. So then I have set up my ODE problem. I have to solve it, and to solve it, I can use a solver. In Julia, you have plenty of solvers for ODEs. I brought here a version that allows this auto switching between solvers that can handle stiffness and non-stiffness. So basically, it automatically detects when my system is stiff and switch the solver accordingly. So I set up my tolerances for solving and also my save at vector. So it's saying that, okay, I will save my outputs every 1 minute, which is given from my training data. So now we can see I can do the plot here of the performance of the UDE without any training, which is terrible as expected. I would have to be very lucky to randomly initialize my weights and get something that is useful. So then I can move on to the training in itself. So if you see here, my differential equation has two dependent variables, right? But only one of the states are observed, which is the fluid phase concentration. I cannot observe solid phase concentration. I'm not aware of any sensor that can measure concentrations in solids. So by this fact, we are only using one of the states of our predictions to compare with the observations. So in order to train the data, as I mentioned, we have to carry out an optimization problem, solve an optimization problem, and we're going to need optimizers. So I'm loading here a couple of libraries. I'm also loading the SciML sensitivity, which allows us to calculate gradients. And you can see here, I'm setting up my predictive function, which has two arguments, the parameters and the states. So this guy here can be an integer because I'm going to show you where it comes in right now. So why I'm building this function? Because at every update of my optimizer, I need to update my parameters. So I'm using the remake command to update the parameters of my original ODE problem. So in this new line here, we are picking up the sensitivity algorithm. This is a very important choice you have to make when you're calculating gradients of differential equations, parameters that are in differential equations. And then you can check the SciML sensitivity library to know guidelines on how to pick the correct joint to not make your system very slow. And here I'm solving the problem with the solve command with appropriate solver, ODE solver. And here I'm using the state integer to say, okay, I just want the first of my states because that's the one I observe. So now I can set up my loss function. So the loss function has an input, my parameters of my neural network. I just make my prediction considering only the first state. And then I compare the observations with my training data. And then I can square them, this difference, and then sum up all the records I have. I also have scaled my difference with respect to the input concentration. So my loss function has no units of engineering units, but it's unitless. So if I try to calculate the loss function with the initial random initialized parameters, I can expect to have a very high loss, of course. And then in order to carry out the optimization itself, I have to set up my optimization problem, which is composed of two arguments, my optimization function and my parameters. So this optimization function is defined from the optimization library. So I have to call the function optimization function. And my optimization function is just a scalar value loss function. And in the optimization function, I have to use the backend to calculate. I have to set up the backend to calculate the gradient. So I'm using here Zygote. So I can also build up callbacks in order to print my loss function every 10 iterations, for instance. And then in order to solve my optimization problem, I need my optimization problem itself, and I need a solver. So the solver I'm using here is a gradient, it's similar to gradient descent, but it has its improvements. It's the adaptive moment estimation. Many people know it as ADAM. And usually the parameters we give to ADAM is the learning rate, which I'm giving 0.075. And I also have to pass the callback if I want my loss functions to be printed every 10 iterations. So I'm training here over 270 iterations. And I can see that my loss function went all over to 12 up to 0.0055 in less than 3 minutes, about 3 minutes, right? 106 seconds. So that's a very decent loss function in a very decent training time for considering I'm doing estimation of parameters inside of a differential equation. So here I can also plot my predictions of my UDE with trained parameters and compare these predictions with my observations. As you can see, we started really bad and we end up after 3 minutes in a very nice estimation, a very good predictions of my observations, in fact. If I did here on the residuals, which is the prediction minus the observation, I would see these probably this very beautiful Gaussian function, right? I also had some test data. So in this, the test data was actually very similar to the training data, except for the fact that I gave inlet concentration of 10 milligrams per liter and allow the system to collect observations up to 100 minutes. So if I use my train UDE with the 20 milligrams per liter signal, I can see that it's able to predict when I do half of a signal as input. So you can see that my system is performing quite well beyond the initial task it was trained for. So here I have to mention as well that, okay, I use the gradient descent base method, but I could start from here as well using what we call a quasi-Newton method to improve my training loss. I mean, the gains would be much smaller than the one I had with this initial training, but still would be able, it would give me a better residuals. So let's move forward. So I have shown you that, okay, I can train my UDE model for this two-dimensional ODE problem in about 3 minutes. If you put neural networks, especially much ones with much layers inside big ODEs, then the training process can be slow. We saw a very small neural network inside a very small ODE, so that's why to run it on in about 3 minutes. So one of the questions we can ask ourselves is, can we speed up the training by warming up the parameters of the neural network? And the answer is yes. And if you remember well from our solid phase mass balance, I have neural network equals derivative. So if I somehow can construct a time series of the derivatives over time, estimate these numbers, then I can move on. I can move from a neural network. I can move from a differential equation to a pure algebraic equation and pure algebraic training of the neural network. So how do we estimate these quantities? So we have only observations of this time series, which is the fluid phase concentration over time. So first of all, we have to estimate Q as a function of time, new time series from my observed states, and then make the derivative of this quantity over time, estimate the derivative. So how do we do this? We just use these mass balance, and we multiply everything by dt, differential time, and then we integrate. And by integrating, the new signal which I want to estimate shows up. And then it is a function of my previous signal, my observation, my observed state, which is the concentration in the fluid phase. I just have to integrate it as well in time. So here I brought some code to do the implementation. So first of all, I imported the data interpolations library because I have observations scattered in time, and I have to have a continuous function to be able to integrate. And I can use also the integrals.jl library. So I'm using the Akima interpolation for my observed fluid phase concentration. And then I can set up also the integral problem. The integral I have to calculate inside all these terms in the expression. So how do I numerically solve integrals in Julia? I just have to build my integrand, and my integrand has to be a continuous function. That's why I interpolated my signal. So then I can set up the integral problem, and I can solve it from 0 to t, the time I want. So I actually built a function as a function of t that solves the integral from 0 to whatever time I want. So I put everything together to be able to estimate my non-observed state from my observed state. And then I can also evaluate this new function at my training timestamps. And I can also visualize. So not yeah, there was a visualization here, which I don't know where it is. It's probably here. So now I have my q of t time series. I can estimate dq dt. So how can I do this? We can use kernel smoothing. So this kernel smoothing is available at DiffQ Flux library right now, if I'm not incorrect. So it's the name of the function is collocate data. I give it my original time series, and I give it my timestamps, and I have to use a kernel function to do the smoothing. And the output of this function is my smoothed signal and the estimation of its derivative. So here I have plotted the original estimation of, in these blue circles, it's the estimated solid phase concentration. And in orange, you can see the smooth version coming out of my kernel smoothing. And also, I didn't plot the derivative, but it was also estimated. One thing you should be really careful when using this collocate data is if you have very sparse points in time, then your estimation of the derivative can be very, very poor. So you have to have a really decent small spacing between your data points to be able to estimate derivatives properly. So then I can set up my learning problem, but now my target is my estimated derivatives, and my features are my equilibrium concentration again, and my observations of the solid phase concentration. Here I can scale my signals to be in between 0 and 1. And then I can set up my neural network, which I call RFast, because meaning that I'm going to be estimating the parameters of it really fast. Once again, I can set up random initialization of the parameters. I build my predictive function. I can build also my loss function, which is the one I want to minimize, which is the difference between my prediction and my observations. The observations being my derivative estimation. I can see that the initial loss is pretty high. And then I can set up my optimization problem and solve it. So if you see here, I'm doing 500 iterations, and I'm able to get it done in less than a second, in 0.14 seconds. And if I take these parameters now and run it inside of my UDE, I can see that with this warm start, I'm able to get a really decent estimation of what would be the predicted liquid phase concentration. So in less than a second, I have a pretty decent model that can roughly explain my observations. And from here, I can take these pre-trained parameters and refine it using the UDE training itself, the heavy training, to improve my observations. And you're probably going to get a much shorter training time than if you do it from random initialized parameters. So let's go to conclusion. So we saw that UDE serves as a powerful tool for enhancing the capabilities of mathematical models, allowing us to extend our simple models to better fit the data. We explored the straightforward implementation of the UDE training for estimating the update kinetics in absorption processes. We also saw how to kind of speed up this training process with this fast two-stage training using kernel smoothing to warm up our neural network parameters. So thank you for your attention. Sorry for the technical problem. And then you can contact me if you want to know more about it. Here's my email, and the code in this demonstration is available at my GitHub, which you can see here in this link. I can put the link on the chat for you if you wanted to. And that's all from my side. Thank you.